Imagine just for a second a universe where matter and light actually aren't the primary building blocks of reality. Instead, picture information itself being the foundational architecture of everything around us. Wild, right? Well, today we're unpacking a really fascinating submission to the core contest for theories of everything. It's this interdisciplinary framework developed by Howard DeLaCruz-Bancroft and mathematical physicist Dr. Prosper Akrobotu, and it seriously challenges some of the most fundamental assumptions of modern science. So let's dive right into this explainer.
This whole investigation kicks off with one incredibly profound question. What if gravity and randomness are actually symptoms of the exact same deeper mystery? Now, normally in physics, we treat gravity, the force pulling massive objects together, and randomness, that chaotic, unpredictable noise in systems, as completely separate phenomena. I mean, they literally live in different textbooks. But what if understanding the delicate relationship between order and randomness exposes a hidden structure sitting right beneath both of them?
To really get how this theory came to be, we kind of have to look back at how it started. The seeds were actually planted way back in 1991 during DeLaCruz-Bancroft's time with the supercomputing challenge at Los Alamos National Laboratory. Fast forward to 2017, and he's back as a tech contractor looking at these 1 nanometer scale electron microscopy images of graphene layers. And he kept noticing these highly specific, asymmetrical anomalies in the graphene. But then 2020 hits. COVID shuts down the labs, scientists are sent home, and physical research basically grinds to a halt. So, forced to pivot, he shifted his research entirely to AI-assisted computational simulations just to try and figure out what was causing those weird anomalies. And honestly, that pivot led to a massive breakthrough that gave us this incredibly cool term, Celominisignum. It's Latin for hidden smallest symbols. What happened was, during those AI simulations, he found that the only way he could consistently reproduce the asymmetrical anomalies he'd seen in the lab was by introducing a viral-like perturbation function into the model. That's when it clicked. He realized he wasn't just looking at random noise. He was looking at recurring patterns of disruption and organization that might actually operate throughout all of nature, across completely different scales. Now, this represents a massive paradigm flip. Traditional physics usually starts with the assumption that matter is primary, right? And that randomness is just this foundational base-level condition of the universe. Well, Celominisignum flips this entirely on its head. It proposes that order and information are primary. Light and material expression, they actually come second. And randomness is demoted to a tertiary process. It basically acts as an invasive, entropy-like disruptor that just introduces variation into systems that are already highly organized. So let's break down how this informational order actually builds from the ground up. The framework has 4 levels. Level 1 is structural order. These are your basic mathematical and physical relationships, things like geometry. Then we move up to level 2, functional order, where systems actively maintain themselves, kind of like your immune system. Level 3 is relational order. This is where independent systems interact to stay viable together, like a whole functioning ecosystem. And finally, level 4 is emergent order, where complex higher-order behaviors arise from all that interaction. Think of things like human intelligence or complex civilization. The key takeaway? Everything builds on information.
But hey, a theory is really only as good as its ability to be tested, right? The authors heavily emphasize that this isn't just philosophy. It's a very real set of interconnected research tools that generate testable predictions. Tool 1 relies on AI-assisted simulation modeling. Since we're dealing with complex relational algorithms here, we can actually use advanced computational environments like Unreal Engine 5. And yes, that is literally the exact same engine used to build a lot of your favorite video games. We can use it to see if these Celominisignum rules actually reproduce emergent structures that match reality better than standard physics rules do.
Let's think about how we'd actually test this. Imagine you're programming a computer game to copy how waves move in a pond. You build 3 different versions, one using standard rules, one using random noise rules, and a third one using these Celominisignum relational algorithms. Then you take all 3 and compare them to a real-life video of a pond. If the game using the Celominisignum rules looks and behaves the most like the real pond, well, you've got solid evidence that these informational algorithms represent actual physical reality. So the absolutely crucial point here is understanding where this organization comes from at the fundamental level. Enter the IMX, or the Informational Ether Matrix Array. And okay, please don't let the big words intimidate you. It essentially proposes a hidden scaffolding framework that exists at the sub-Planck level, which is way smaller than anything we can currently measure. It acts as a sort of new zero, a foundational reference structure that bridges pure informational potential with the physical reality we can actually observe and measure every day. If that still sounds a bit abstract, let's ground it with an analogy.
Imagine two groups of people, and they're both trying to build something out of Lego blocks. One group gets clear, step-by-step instructions. The other group, no instructions at all. Obviously, the group with the instructions is going to build something far more stable and recognizable. In this theory, the IMA is exactly that. It's that hidden set of instructions. It's the underlying framework that helps physical reality organize itself, instead of just collapsing into random chaos. Building right on top of that scaffolding, we have tool 3, relational coupling and decoupling. This looks at the exact dynamics of how systems manage to stay together or break apart under stress. And by stress, we mean physical forces like heat, pressure, or sudden energetic impact. The framework proposes that particles, forces, and fields remain stable when their parts stay coherently coupled, which basically just means deeply connected and coordinated. But when that relational coherence weakens, the system begins to decouple, transforming or eventually degrading. To make this a bit more intuitive, picture a group of people standing outside in a violently heavy storm. The group that holds hands tightly and moves together, that's a strongly coupled system. They survive the stress. But if they start letting go of each other, that's decoupling. The structural integrity fails, and they just scatter. Celominisignum proposes that this exact dynamic governs the stability of literally everything, from tiny subatomic particles all the way up to incredibly complex biological systems. Now, you might be wondering, how do we actually measure how well a system is holding hands? That's where the IAC, or the Informational Alignment Coefficient, comes in. This is a proposed metric used to measure whether the different parts of a system are aligning their rules toward a shared, coherent goal. It's pretty straightforward. A high IAC means high alignment. A low IAC means there are conflicting or totally random rules operating within the system. Let's look at this in action. Think of two different soccer teams. A team with a high IAC listens to the coach, executes passes flawlessly, and operates as a single, perfectly coordinated unit. They use their energy efficiently and just make way fewer mistakes. On the flip side, a team with a low IAC is really just a bunch of players running around aimlessly, ignoring each other. By applying this specific coefficient to simulated physical systems, the authors predict that highly aligned systems will transfer information more efficiently and resist destabilization much better than low alignment systems. But what happens to a system over a long period of time? For that, we use the IOC, the Informational Order Coefficient. This one measures persistence. It basically asks, how does a system maintain its core identity even when its physical components are slowly changing or decaying away? Celominisignum argues that a system's identity persists not because the physical parts remain exactly the same, but because the coherent relational organization is what's being preserved. Think of it like a school. If you were to change all the teachers, the students, the schedules, and the rules completely randomly overnight, well, it feels like a totally different school, right? It has lost its identity. But if you replace just one classroom at a time very gradually, while keeping the core relationships and the culture intact, it fundamentally remains the same school. A high IOC allows a system to survive that kind of gradual replacement by preserving the underlying organizational structure. Okay, let's dive into this next concept because I'll admit it might sound a little counterintuitive at first. Chirality. In this particular framework, chirality isn't just about left or right-handed molecules like you might remember from chemistry class. It's a mechanism of informational asymmetry. It suggests that introducing slight, carefully constrained differences into a highly ordered system actually prevents destructive resonance. In other words, having absolute perfect symmetry can actually be a fatal flaw. Here is exactly why that matters. If you build a bridge with perfectly symmetrical, identical repeating patterns, a strong wind or a harmonic vibration can easily compound upon that perfect repetition. It builds up destructive resonance, and it can literally tear the bridge apart. But if you introduce controlled asymmetry, just slight, intentional differences throughout the structure, those differences interrupt the resonance and dissipate the energy safely. So, constrained asymmetry actually preserves adaptive stability. So you're probably asking, what is the ideal balance between order and variation? Well, the framework points directly to the golden ratio, specifically an 8:5 proportion, as the ideal indicator of relational equilibrium. It suggests that long-term stable systems simply don't emerge from maximum order or maximum randomness. Think about a stack of blocks. A perfectly neat stack might actually be too brittle, and a completely messy stack will just fall right over. But a stack organized with a dominant structure, yet flexible enough to adapt, an 8:5 ratio of order to variability, that's the one that survives stress the best. Now, here is where this theory gets truly mind-bending and connects right back to gravity and space-time. Working alongside mathematical physicist Dr. Prosper Akrobotu, the researchers developed SET, the stress-energy information tensor.
This proposes extending Einstein's conventional stress-energy mapping to actually include informational structure. It seriously suggests that gravity itself might act as an emergent, coherence-preserving relational process.
For all the math enthusiasts out there, the crucial point is the integration happening here in the equation. In traditional physics, the standard stress-energy tensor is represented by T, but SCIT introduces a brand new variable, psi, representing informational structure. This mathematically integrates the idea that mass energy plus informational organization might actually work together to contribute to space-time curvature.
Let's try to make that abstract math a bit more concrete. Imagine you have two massive Lego cities. Both cities are made of the exact same number of bricks, meaning they weigh the exact same amount and have the exact same mass. But one city is carefully organized with complex, interconnected roads and structural systems, while the other is just a giant randomized pile of bricks. Seat asks a truly fascinating question. Could the way those bricks are organized matter to gravity just as much as their total weight?
What really makes this entire submission to the core contest so compelling is the author's absolute insistence on falsifiability. The researchers firmly insist that science advances not by protecting ideas, but by constantly challenging them. They aren't presenting Celominisignum as some finished, untouchable dogma. Not at all. They're offering it as a set of interconnected research tools that generate highly testable predictions. And if the AI simulations and real-world experiments don't back it up, they welcome its failure. The next step belongs entirely to the evidence.
Which really leaves us with this massive, deeply provocative question. Are hidden informational relationships the true fabric connecting reality itself? Because if Celominisignum is right, the universe isn't just a random collision of particles that occasionally form something interesting. No, it's an incredibly complex, interconnected network of information where order is the rule and chaos is just the exception. I really hope this explainer sparks some curiosity for you today, and I highly encourage you to keep questioning the fundamental nature of the cosmos. Thanks so much for joining me.